Today, we will solve a calculus problem. A pool is being filled with water, and we want to know how fast the water is rising when it is 5 feet deep. We also know the pool is 20 feet wide, along with other dimensions seen in the diagram. Finally, we know the pool is being filled at 1.4 cubic feet of water per minute. This is a related rates problem. We want the rate of change in one thing based on the rate of change in something else. Typically, this is change over time, that is, the derivative with respect to time. Let's examine our question in greater detail. What we're being asked for is the rate at which the water's height is rising, call it h. In other words, the derivative of height with respect to time, dh dt. And we are given two clues. The rate at which the volume V of water is increasing, dV dt, and also the height of the water at that moment in time, h equals 5 feet. Our approach for related rates is to create a formula for volume in terms of height, V of h. Then we take the derivative with respect to time to get an equation with everything, the things we were given, dV, dt, and h, and also the thing we're looking for, dH, dt. Let's set up a formula for volume in terms of height. We already know the width of the pool and the water is 20 feet, so we just need the area of the water, A. Now, since the height is 5 feet, we can ignore everything above the 6-foot mark. And now we have a trapezoidal area that we can break into sections. Let's look at them. Area 1, or A1, is a triangle. A2 is a rectangle, and A3 is another triangle. Now, really, we have two sets of areas. The water areas in red with a common height of h, and the pool areas in black with a common height of 6 feet. We will label that height big H. Let's look at A1. It would be really helpful if we knew the water length. Let's call it L1 for now. What we do know are the pool height and the pool length from the diagram. Big H is 6 feet, and big L1 is also 6 feet. Now, it looks like we're stuck, but let's use our knowledge of trigonometry. These two right triangles share the same angle there at the bottom. Let's call it theta. And if it's the same angle, then it must have the same tangent, which is the opposite side over the adjacent, length over height. So we know the water length over the water height is equal to the pool length over the pool height, which is 6 feet over 6 feet, and simplifies to 1. So L1 is equal to H. Now we take the formula for the area of a triangle. A1 is 1/2 base times height. And since the base is the length L1, we can substitute h in its place to get the result 1/2 h squared. On to area 2. Our water area, A2, has a height of h, and it also has the same length as the pool rectangle, a length of 12 feet. So A2 is equal to length times height is equal to 12h. Simple. Last but not least, we have the final area, A3. Now this is just the same situation as before. Two triangles sharing the same angle, which have the same tangent. So water length over water height is equal to pool length over pool height. From the diagram, we know that's 16 feet over 6, which is 8/3. So the water length is equal to 8/3 the water height. We substitute that into our formula for the area of a triangle, and we have A3 is equal to 1/2 base times height is equal to 4/3 h squared after substitution. So now we've done the setup, let's find the solution. The total area of water is equal to the first area plus the second plus the third. Now we substitute our formulas into there, and the result simplifies to 11/6 h squared plus 12h. Now we build our formula for volume, which is width times area. The water's width is 20 feet, and its area is 11/6 h squared plus 12h, which simplifies to 110/3 h squared plus 240h. So, we've built our formula for volume in terms of height, v of h. Now, we need to derive it with respect to time. The thing is, we only know volume in terms of height. So how do we derive it with respect to time? For that, we need the chain rule for derivatives. The derivative of volume with respect to time is equal to the derivative of volume with respect to h, height, times the derivative of height with respect to time. You might also see the chain rule written like this, with v prime and h prime, but it's the same idea. So, we need the derivative of v with respect to h. That's the derivative with respect to h of the formula we built, 110/3 h squared plus 240h, all multiplied by the dh dt at the end. Now, that's just the derivative of a polynomial. That's easy. We split up the sum and pull out the coefficients, and so we have 110/3 times the derivative with respect to h of h squared plus 240 times the derivative with respect to h of h. Well, those two derivatives are just 2h and 1. So our result simplifies to 220/3 h plus 240, all multiplied by dh dt. dh dt is the thing we want, so let's use algebra to solve for it on one side of the equation. dh dt is equal to dv dt times 1 over 220/3 h plus 240. And now we can insert the values we were given. dv dt is 1.4 cubic feet per minute, and h is 5 feet. You can throw this into a calculator right now, or you can simplify the fraction to 3 over 1,300. In either case, this is our approximate result. The question asks that we round it to 5 decimal places, so we have our answer. At the moment the water is 5 feet deep, it is rising at approximately 0.0023077 feet per minute. Thank you for watching.